Okay, good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Dr. Jingrui He, Professor and MSIM Program Director, School of Information Science from University of Illinois, Urbana-Champaign. The talk title is Multifaceted Robustness and Transfer Learning. Dr. Jingrui He received her PhD from Carnegie Mellon University in 2010. Her research focuses on heterogeneous machine learning, active learning, neural bandits, and self-supervised learning with applications in security, agriculture, social network analysis, healthcare, and finance. Dr. He is a recipient of 2016 NSF CAREER Award, the 2020 OAT Award, 3 times recipient of the IBM Faculty Award in 2018, 2015, and 2014, respectively, and was selected as IJCAI 2017 Early Career Spotlight. Dr. He has more than 170 publications at major conferences, including NeurIPS, ICML, ICLR, KDD, and journals, TKDD, JMLR, TKDE, and is author of 2 books. Her papers have received the Distinguished Paper Award at FACT 2022, as well as the Best of the Conference at ICDM 2016, ICDM 2010, and SDM 2010. She is the Distinguished Member of the ACM, a Senior Member of AAAI and IEEE. She's also the Program-Co-chair of IEEE BigData 2023. Dr. He, it's a great honor to have you as part of UND's Distinguished Webinar Series. So thank you so much for taking the time to do this webinar for us. It's a great honor. So the floor is yours.
Great. Thank you so much, Prakash, for the nice introduction and also for inviting me. Before I get started, everybody can hear me okay. Is that correct?
Yes.
Okay, great. So welcome, everyone. So my name is Jingrui He. And today, I would like to talk about multifaceted robustness in transfer learning. So to follow the tradition, I would solicit questions at the end of my talk. And during my presentation, if you have some clarification questions, feel free to raise your hand. I'd be happy to answer them. So let me start with the basics of supervised machine learning. Here, the basic assumption is that the training and test data follow the same distribution. In this way, the generalization performance is typically in proportion to the number of labeled training examples. In other words, the more labeled training examples we have, the better the generalization performance in terms of, say, the classification error. And in the figure on the bottom, we see an illustration of the supervised machine learning. And on the left-hand side, we have a couple of input samples in the form of, say, the quick draw images. And then on the right-hand side, we have a bunch of output labels such as banana, ant, and baseball. The goal of supervised machine learning is to identify this input-output relationship in the form of y is equal to f of x. Can you see my mouse here?
Yes.
Oh, okay, great. So from supervised machine learning, researchers have further worked on transfer learning, which is a closely related problem setting. Now, the problem definition of transfer learning is the following. We're given one or more source domains. It could take a variety of different forms, which I will come back in a little bit, as well as the target domain with very little label information or no label information at all. Our goal is to learn a prediction function on the target domain using the knowledge from source domains. So, like I said, the source domains can be presented in a variety of different forms. For instance, in the figure on the left-hand side, the source domains are presented as pre-trained source models such as ChatGPT, Llama. And on the right-hand side, the source domains are presented as various kinds of public source datasets. So up until now, transfer learning has been successfully applied in many real-world applications, and here I have provided a few examples. The first example is in computer vision, where we work on image classification, and the source domain could be a couple of quick draw images, and the target domain could be the real world images. The second application is natural language processing for sentiment analysis. And here the source domain would be the analysis of book reviews, and a target domain could be the analysis of electronic product reviews. The third application, the third example is in graph mining, where we focus on traffic flow prediction. Here, the source domain would be the traffic flow prediction for the city of Chicago, and the target domain would be a similar problem, but in the city of Anaheim. And the fourth example I use here is for agriculture analysis, where we focus on plant phenotyping. And here the source domain would be, say, yield prediction for the state of Illinois, and the target domain would be the yield prediction for Nebraska. Okay, so although a lot of the transfer learning methods have been proposed so far, many of them are vulnerable to adversarial attacks. One example is the poisoning attacks on the source domain, and another example is the Byzantine attacks in a closely related problem setting called federated learning, which I will come back in a little bit. So if we look at the figure on the bottom, we will see how poisoning attacks works in a setting of transfer learning. In these three figures, the solid circles and triangles represent the two different classes in the source domain. The gray circles and triangles represent the two classes of examples from the target domain. Finally, in the middle, we have the hollow circles and triangles. They represent the poisoned source examples to be added to the source domain. Let's first take a look at the first figure on the left, all right? In this figure, we only have the clean examples from the source domain, based on which we can construct the predictor model, which is illustrated by this gray dashed line. In this case, because the source and the target domains are very similar to each other in terms of the distribution of examples from the two classes, this predictor model would perform very well on the target domain as well. However, in the middle, we have added, in addition to the clean source examples, we have added a couple of poison examples to the source domain. Again, they're indicated by the circles and the hollow triangles. With these added poison examples to the source domain, then the predictor model that we can get from the source domain will be shifted from the original gray dashed line to this black dashed line, as you can see in the figure on the right-hand side. So in this case, if we were to use the same predictor model in the target domain, it wouldn't be performing very well, meaning that the transfer learning algorithm is suffering from such poisoning attacks. Another kind of vulnerability of transfer learning existing techniques is due to complex distribution shifts. So the transfer learning algorithm, the existing techniques, they are designed to model the distribution shift. However, for rich data, such as graphs, oftentimes we have complex distribution shifts, indicating the coexistence of multiple types of distribution shifts. Here, I have provided two specific examples. One is called the node attribute distribution shift. The other one is called graph structure shift. So the table on the bottom of this page illustrates the two kinds of distribution shifts, or the complex distribution shifts. The second column, the first graph is the source graph, okay, with all the nodes in blue. The second graph with all the nodes in yellow is the target graph. Between these two graphs, we can see that the graph structure remains the same between the source and the target. But if we were to look at their attributes, which is indicated by the panel of squares, okay, we can see that the attributes have changed. The distribution of those attributes have shifted from the source to the target. So this is what we mean by the node attribute distribution shift. The last column, on the other hand, illustrates the graph structure shift, where the first figure on the top, again, is the source graph, and the second figure on the bottom, this is the target graph. Between these two graphs, we can see that the graph structure has changed to some extent. but the underlying distribution for the node attributes roughly remain the same, okay? And like I said, for rich data such as graphs, we might have the combination of multiple types of shifts, including node attribute shift and graph structure shift. And a lot of the existing transfer learning techniques are not capable of handling such complex distribution shifts. I see a question in the chat. Let me read it out. How do you figure out which particular model and fine-tune to take advantage of when selecting your applicative use, say NLP? So if I understand correctly, this is about picking the correct model for a specific downstream application. First of all, we need to look at the kind of data that is available in a certain application. If the data is single modality, where we expect to see just one type of distribution shift, then a lot of the existing techniques, such as those based on invariant representation learning, which I will introduce in a little bit, could be used. And on the other hand, if we are facing rich data, such as graphs or even the more complicated temporal graphs, then we need the more sort of powerful tools capable of handling the complex distribution shifts. And also, if there's domain knowledge or prior information regarding whether or not there exists some kind of adversarial attacks, then you can decide if we want to use just some existing transfer learning techniques, or you want to employ the ones that are robust to such adversarial attacks. Does it answer your question, or is there any follow-up from this? Okay, in that case, I'm gonna continue with the rest of my presentation. So here's a roadmap of my talk. I briefly introduced the background of transfer learning, as well as the different kinds of vulnerabilities of existing transfer learning techniques. Next, I would like to dive into more details regarding the two types of vulnerabilities, starting from the adversarial vulnerabilities. At this point, we all know that the deep learning models are vulnerable to noise, basically. Okay, so for instance, on the left-hand side, we can see how the adversarial noise, when added to an image, could dramatically change the predicted label for that image. On the other hand, even for some publicly available data sets, source data, there can be some noise in it due to, say, the labeling, mislabeled information, as you can see on the right-hand side. So the first piece of work I would like to introduce is exploiting this kind of vulnerability of a lot of existing transfer learning techniques. And this has been published in KDD in 2021 and TKDE in 2023. Let me start with the formal problem definition of the poisoning attacks that we design in transfer learning, basically to exploit the vulnerability of existing transfer learning techniques. So here we're given a base algorithm for transfer learning, okay? We're given some labeled source data as well as some unlabeled target data. Our goal is to degrade the overall prediction performance on the target domain. In particular, in this work, we study a specific kind of attack, which is the poisoning attacks. And to this end, we want to achieve the following two goals. The first one is indirect, and the second one is invisible. So this is the same figure that you have seen a few slides back. By indirect, we mean that we can only manipulate the source data. We cannot manipulate the target data. On the other hand, by invisible, we mean that the attack, the added poisoned examples to the source domain cannot be easily noticed by the users, okay? So for instance, if your source domain originally is class separable, as you can see in the figure on the left-hand side, okay, we can use a linear model to separate the two classes of examples in the source domain. Then after we add the poison source examples, we want the source domain to be class separable, to remain class separable. In this way, we say that the attack is invisible. We want to achieve both of these goals in our attack mechanism. So before diving into details regarding our proposed attacking mechanisms, I would like to take a detour and briefly talk about the unified generalization bound of transfer learning. In this work, we have focused on a specific type of transfer learning techniques, which is called invariant representation learning. With invariant representation learning, what we do is we map all the examples from the source and the target to a common latent representation space where the distributions of the source and target would be very close to each other. And then we would identify a single predictor model that's expected to perform well on both the source and the target. Okay, now, a lot of the invariant representation learning algorithms can be summarized as minimizing a unified objective function, as you can see in the equation on the top. Here we have two terms, where the first term is the empirical loss in the source domain, and the second term is some kind of distribution discrepancy between the source and the target in the learned representation space. So for these algorithms, by minimizing this particular objective function under the covariant shift assumption, which is to say that the posterior probability of the label y given x, okay, say the sentiment of an article given the content of the article, this distribution remains the same between the source and the target domains. In this case, we can prove that the generalization performance of these transfer learning algorithms in the target domain in the form of the target prediction error is bounded by the sum of three terms, which you can see in this inequality on the bottom. On the right-hand side, the first term is the prediction error on the source domain. The last term is the combined error of the ideal hypotheses. But I would like to focus on the middle term, D of PSX, PTX. This denotes the marginal domain discrepancy between the source and the target. Notice that I mentioned this is the marginal discrepancy, meaning that when evaluating this discrepancy, we only take into consideration the features in the learned representation space and not the labels. This sometimes can cause problems in the setting of transfer learning, which I am illustrated in this page. So we have three groups of figures. Let's first take a look at the group on the left-hand side. In the top figure, we use two circles, blue circles, to represent the two classes of data in the source domain, and two orange circles to represent two classes of data in the target domain. When we compare these two domains, we can see that there is only very small distribution shift from the source to the target. In this case, after we map both examples to this learned representation space, we can easily find a common predictor model, which is this red dashed line that performs well on both the source and the target. The group of figures in the middle illustrate the scenario where we have moderate distribution shift from the source to the target. And in this case, we're still able to find a latent representation space where the source and target would share the same predictor model. However, things would change if we have large distribution shift from the source to the target, as you can see in the top right figure, where the source examples in the two blue circles are kind of deviating from the two orange circles. In this case, if we only use the marginal domain discrepancy, as I introduced in the last page, after we map all the examples to this latent representation space, it could be the case, very likely be the case that the predictor model that works well on the source domain would work very badly in the target domain due to this large distribution shift and the use of the marginal domain discrepancy. So based on these observations, we proposed indirect invisible poisoning attacks, or I2 attack for short, basically achieving our goal by satisfying the two requirements of being indirect and invisible. On the high level, the objective function of I2 attack is to maximize the label-informed distribution discrepancy. So this is in direct contrast to the marginal discrepancy that I talked about earlier. And we want to maximize this label-informed distribution discrepancy between the poisoned source data and the original source data. So this attack can be summarized into this bi-level optimization problem, as you can see on the bottom. For the outer optimization, under some perturbation constraint, we want to maximize the label-informed domain discrepancy. The main difference between this label-informed domain discrepancy and the marginal discrepancy is in terms of the use of labels when evaluating the difference between two domains. So this is illustrated in the two figures on the right-hand side. So before the attack, we can see that in the top figure, the source and the target, they have a lot of similarity in terms of the underlying distributions for the two classes of data. However, after the attack, by including some poisoned source examples, after we map all the examples to this learned representation space, the source and target would be quite different. So this would lead to the failure of many of the existing transfer learning techniques. The previous formulation in terms of the bi-level optimization is a generic formulation in the sense that we can use a variety of different Bayes algorithms for transfer learning. And here I am providing a specific instantiation of I2 attack with the Deep Adaptation Network, or DAN, as the Bayes algorithm. DAN is an example of the invariant representation transfer learning technique. It's basically learning the domain invariant representation in the latent feature space. And for DAN, the specific domain discrepancy used is called maximum mean discrepancy, or MMD for short. And so on the bottom, I have provided more details regarding MMD. In order to compute MMD, the first step, we need to identify a kernel mapping from the original feature space to calligraphic letter H, which stands for the reproducing kernel Hilbert space. Then, based on this kernel mapping, we obtain the mean embedding of a distribution in this reproducing kernel Hilbert space. Finally, the distance of two distributions is simply computed as the distance of the mean of their mean embeddings. Okay. Now, with DAN, then the I2 attack can be formulated as what we have on the left-hand side. And again, on the top, we are maximizing the label-informed domain discrepancy in this case because DAN is used as the Bayes algorithm. So the specific form would be the label-informed MMD. And again, comparing the label-informed MMD and the marginal MMD, the main difference is in terms of the use of the label information when calculating the distance between two domains in the labeled version. Okay, so in this way, we're able to sort of avoid the situation, as you can see a couple of slides back, when the distribution shift from the source to the target is pretty large. In addition to DAN, our I2 attack can be used together with many other invariant representation learning algorithms. And this table provides a few specific instantiations using DAN, Coral, DAN, and so on and so forth. The third column provides the original objective function in these invariant representation learning algorithms. And then the last column is the attacking function, maximizing some kind of label-informed domain discrepancy. And the intuition is that we want to enforce the distribution misalignment between the raw and the poisoned source data. Next, I would like to provide some empirical results demonstrating the effectiveness of our I2 attack. Okay, and here, this table summarizes the comparison results. The rows in the middle, they are the performance with the base model called DAN, okay? And then the last few rows, they are the associated with the performance after we have performed the I2 attack with DAN as the base model. For the evaluation metrics, we have considered the source accuracy. The domain discrepancy measure in this case is the marginal domain discrepancy, not considering the label information, and the target accuracy. Based on these comparison results, we have the following observations. Number one is that the target classification accuracy significantly decreases. Now, the target accuracy is the set of numbers highlighted in red. Before the attack, using DAN, we have pretty decent target accuracy, okay, in the 70%, 90%, and so on and so forth. However, after the attack, if we look at the target accuracy, they're all pretty small, especially in comparison to the base model, the target accuracy using the base model only. I see another question. At a high level, what's the difference between DAN and DAN here? That's a very good question. So both of them belong to the invariant representation learning category. Okay, let me go back to the previous page. So this row is corresponding to DAN, and this row is corresponding to DANN. The difference is in terms of the specific domain discrepancy measure used in their objective function. For DAN, we're using the maximum mean discrepancy, which I briefly introduced a few slides back. With DANN, we're using the JS divergence, which is shown here. And the same applies to the other algorithms listed in this table. They're basically minimizing the sum of both the empirical error in the source domain and some notion of the domain discrepancy. Okay, thank you again for this question. Let's come back to the evaluations. So we have seen that in terms of the target accuracy, I2 attack is pretty effective. Also, since we are directly manipulating the source domain, this is called the indirect attacks. The second observation from this table is that the source domain remains class separable. So let's look at the numbers highlighted in red. Before the attack, the source accuracy are all very close to 100%, indicating that in the source domain, the different classes are separable. After the attack, we can see that the source accuracy remains very high, if not at 100%. So the attack, although it's able to make the target accuracy lower, it keeps the class separable property of the source domain. And the last observation is that if we look at the marginal domain discrepancy, say MMD, in the context of the DAN model, it stays pretty much the same. Okay, again, this is reflected by the numbers highlighted in red. This observation, together with the fact that the source domain remains class separable after we have added the poison source examples, indicate that our proposed attack is invisible, not noticeable by the users. So these are only the results using the DAN model. We have actually observed the similar performance using the other base algorithms. In this case, a natural question to ask next is, are the attacks universal across models? More specifically, can the poison examples generated by I2 attack with DAN as the base model be applied to attack DANN, which is a different base model? The table in the middle provides the answers to this question. So in the 3 columns in the middle, we have the results of DAN before and after the attack. We observed the similar results as shown in the previous slide. If we were to use the poison examples generated in this setting to attack the DANN model, then we can see that the target accuracy is again much lower than before, which is highlighted in red in the very last element of the table. And in terms of the source accuracy and the marginal domain discrepancy after the attack, those numbers are very similar as compared to before the attack, even though the poison examples were not generated using I2attack DANN. The implication from these results is the following. Our I2attack is able to perform the black box attacks without accessing the transfer learning algorithms. Yet another related question is, are the attacks universal across target domains? More specifically, we want to know if the poison examples generated by specific transfer scenario, say from B to I in the image cleft dataset, be used to attack other target domains. Again, I'm using the results in the table here to answer this question. The middle three columns provide the results of different transfer scenarios from B to I, B to C, and so on and so forth. We have their source accuracy, target accuracy. And then the last three columns shows what happens after we use the poison examples generated in the first setting from B to I. In this case, across all three scenarios from B to I, B to C, and B to P, we observed a dramatic decrease in the target accuracy, while the source accuracy and the marginal domain discrepancy remain roughly the same as before. So the implication from these results is the following. Our I2attack is able to perform black box attacks without having access to the specific target domain, as long as there is some similarity among those target domains. So that's all about the first work exploiting the vulnerabilities of transfer learning to adversarial attacks. Next, I would like to talk about a closely related problem setting to transfer learning, which is called federated learning. As many of you might know, in federated learning, instead of having, say, typically one source domain and one target domain, we might have N clients collaborating to train a machine learning model under the orchestration of a central server. These clients can be considered as domains. And the benefits of doing so is that those clients don't have to share their raw data. Okay. Instead, they would share the knowledge across different clients, between the client and the server, and so on and so forth. One standard algorithm for federated learning is called a FedSGD, which proceeds in multiple communication rounds. So for each communication round, first of all, the server would broadcast the parameters of this global model to all the clients. Then each client would compute the gradient based on the local data and sends back to the server the gradient computed using the local data, which we call the honest gradient. The server then would aggregate the gradients from all N clients using, say, the average aggregation and update the model parameters for this global model accordingly. Like transfer learning, federated learning is also vulnerable to adversarial attacks and failures. More specifically, some of those clients might have corrupted data, or they might upload malicious gradients. Now, these behaviors can cause suboptimal convergence or even divergence of the parameters for the global model. In particular, in our work, which was published in 2024 at AI Stats, we focused on Byzantine attacks. For these attacks, the malicious clients would send arbitrary gradients to the server, again, causing the suboptimal convergence or even divergence of the global model parameters. I see another question here. Why are we assuming client 1 through K are source? Wouldn't they have different distributions? That's a very good question. The clients would have different distributions, which we would call the non-ID setting, and I would provide more details in a little bit. When we say client 1 through K are considered a source, this is from the perspective of, say, the K plus 1's client. In other words, if we have 11 clients in total, if we focus on client 11, then clients 1 through 10 could be considered as the source. but eventually everything is operated under the federated learning framework. And that's the difference between this particular problem setting and transfer learning, in particular, the multi-source transfer learning. But that's a good question. So let's continue with our discussion here. In the presence of those attacks, such as the Byzantine attacks, researchers have proposed various robust aggregation rules, or AGRs for short. The key idea is to replace the average aggregation, which I've shown in the previous slide, with a robust estimator of the true gradient. On the bottom, I provided a simple one-dimensional example of such an aggregation. For the input data, we have a bunch of numbers. You can consider them as the gradients that have been reported to the central server. All these numbers have very small absolute values except for the last one, which is associated with the Byzantine. So for these gradients, their true mean should be exactly 0. However, if we just use the average aggregation, we would get 12.5, which is much bigger than the true mean. On the other hand, if we were to use a robust estimator, say the median, the obtained estimation is 0.05, which is very close to the true mean of 0. However, these AGRs, these existing robust aggregation rules, they work well in the IID setting, but not so much in the non-IID setting. So what do I mean by the non-IID setting? It means that even among those honest gradients, okay, their respective gradients, G sub I and G sub J, with IJ being the indices of those clients, if we were to take their expected value, they are not the same. More specifically, in our work, we have introduced the notion of C-label skewness to characterize the different label distributions. Okay, the next question is, so client K+1 will be the target data as mentioned in transfer learning. That's a good question. So each client would take turns to be the target data. So from each client's perspective, it is the target, and then the other clients would be the source. Coming back to our C-label skewness, in this notion, we assume that the data distribution for each honest client can be expressed using the equation in the middle, where P sub I is the data distribution for the ith client. And then C, lowercase c, is the total number of classes. Z is a label, all right? And then P sub IZ is the label distribution of client I with respect to class Z. And finally, Q sub Z would be the class conditional distribution for the class Z. With this notation, with this notion of the data distribution, different clients, we assume, would share the same class conditional distribution, Q sub Z, but they would have different label distributions in terms of P sub IZ. With this definition of C-label skewness, we have the following observations. Let's first define the honest simplex, which is a simplex spanned by all C expected gradients. So these expected gradients are represented as E of gamma Z. This denotes the expected gradient computed with data from class C. So we would have C of them, and the simplex is expanded by all those expected gradients. With those expected gradients and the simplex, we have the following observations. Number one, if we look at the honest clients, their gradients expectations would be distributed exactly on the honest simplex. On the other hand, if we look at the actual observed gradients from those honest clients, they are distributed very close to the honest simplex. To provide some evidence regarding these findings, we have used the MNIST dataset where the number of classes is 10, and we have performed PCA of the honest clients under the two problem settings, under the two algorithms of FAD-SGD and FAD-average, where the results are presented in the two figures in the middle. No matter which algorithm is being used, we can see that over 99% of the variance would concentrate on the first C-1, which in this case is 9 principal components. And this verifies our two findings mentioned earlier. Based on these findings, we have proposed a BOBA algorithm, which stands for Byzantine Robust and Unbiased Aggregator. This is essentially a two-stage process where in stage one, we try to find the honest subspace. Notice that in this stage, we find the subspace only, not the simplex. Then we project all the gradients to this subspace. Whereas in stage two, we find the honest simplex based on the subspace, reconstruct the label distribution for each client, and then drop the clients with abnormal label distributions, which are likely to be Byzantine. This two-stage process would have different impacts on honest versus Byzantine clients. More specifically, with this approach, all the honest gradients would be kept. On the other hand, for the Byzantine gradients, they're either weakened through stage one or discarded via stage two. And these different kinds of impacts are illustrated in the figure on the right-hand side. On the top, we have two Byzantine gradients represented as orange axis. They have been discarded in stage two of our BOBA algorithm. For the two remaining Byzantines, again, they are the orange axes. They have been weakened through stage one by doing this kind of projection to the subspace. This set of figures provides the illustration of how BOBA works. At the very beginning, we have a set of honest gradients represented as the blue pluses, and a set of Byzantine gradients represented as the orange pluses in the first figure. In addition, we assume that we have limited amount of data on the server based on which we can obtain two gradients called server gradients represented as the green triangles. Using the two green triangles, we can come up with the initial subspace, which is indicated by the red line in the first figure. Following that, we're going to perform two steps until convergence. In figure two, we're going to identify the nearest client gradients, which are highlighted by this purple circle. And following that, in figure three, we would update the fitted subspace based on all the nearest client gradients. These two steps will be repeated until convergence. Finally, we would have the final fitted subspace as indicated in the fourth figure. At this point, we would project all the gradients to this fitted subspace. So in the fifth figure, after we have done with all the projections, we would go ahead and estimate the honest simplex, which is represented by the red line segment. And finally, we would drop the gradients whose projections to this simplex are out of, basically their projections to the subspace are out of this fitted simplex. So they're likely to be the Byzantine gradients. BOBA, as compared to existing AGRs, has a lot of benefits and advantages. The first one is being unbiased, meaning that is able to reduce the selection bias of many other robust AGRs. I think in the interest of time, I'll probably go a little bit faster for the remainder of the slides. So these three figures compares BOBA with an existing robust federated learning algorithm called CRUM. In particular, in these figures, the blue pluses, they represent the honest gradients. The green dot represent the true gradient, whereas the red circle, the red square represent the aggregation result. The CRUM performs well without the attacks on the ID clients as shown in the first figure, but with non-ID clients, which is the focus of our work, its performance is bad. As you can see in the middle figure, the red square is far away from the green dot, whereas using BOBA, the estimation of the gradient is very close to the true gradient as shown in the last figure. Another benefit of BOBA is robustness, meaning that it's able to decrease the vulnerability of other robust AGRs. In these three figures, again, we're comparing with CRUM, the existing robust federated learning algorithm. And in these figures, we focus on this orange region, which is the range of aggregations given different Byzantines. Similar as before, Chrome performs well with IDE clients with the Byzantine text. However, if the clients are non-IDE, then its estimation of the gradient is deviating from the true gradient in all different directions, resulting in a very large orange region, whereas using boba, even with non-IID clients, our orange region is pretty small. So I'm going to skip this page and talk about the results. So we have evaluated boba in 3 different scenarios using multiple model architectures on different data sets. And the first aspect we want to evaluate is in terms of boba's unbiasedness. And the results are presented in the table on the right-hand side, where the last row is boba. In this experiment, we didn't include any Byzantine text. The key observations are, number 1, boba's performance is very close to average without the attacks. Second, compared to the other AGRs, it has the smallest MRD, which stands for max recall drop. The smaller, the better. And this table shows the comparison results in the presence of Byzantines. Again, the last row is corresponding to our boba algorithm. As we can see across all 3 datasets, all the different scenarios, boba significantly improves the worst case accuracy on those datasets as compared to state-of-the-art. That's all about the first type of vulnerability with respect to the adversaries. Next, I'd like to very briefly talk about the complex distribution shifts. In the previous work, researchers have studied the use of Gaussian process to model transfer learning on IID data. In this case, it's not really a complex distribution shift, but rather a single one. You can consider that as the attribute shift. So one thing I would like to highlight here is the design of the transfer kernel, which depends on this hyperparameter lambda, indicating the similarity of different domains. From this work, a natural question is, can we automatically tune the hyperparameter to reflect the domain similarity? One of our early works published at NeurIPS 2022 answered this question with a new distribution-informed neural network. And under certain conditions, we're able to show that this distribution-informed neural network is essentially a Gaussian process where the transfer kernel is decomposed into both the sample level kernel and distribution kernel. One thing I like to highlight is that this distribution kernel is a counterpart of the hyperparameter lambda that I indicated before, reflecting the similarity between different domains. However, in this case, we are sort of estimating the similarity based on the data, not just using a hyperparameter lambda, which has to be decided by the user. So far, we're still focusing on the IID data setting, where we could have just one type of distribution shifts. Now, from IID data to non-IID data, if we want to extend the previous work in terms of the use of Gaussian processes, we need to consider a different data generation process. And in our work, we use a 2-stage generation process, first generating the graph distribution, and then generating the specific nodes. Then, extending upon our previous work called distribution-informed neural network, we have further proposed the structure-aware neural network by learning both the local node representation and then the global graph representation. Skipping the details, eventually we're able to show that this structure-aware neural network is also equivalent to a Gaussian process, where the first part, sigma sub w squared, is a constant. The second one, the node level kernel, is able to accommodate the distribution shift, whereas the last one, between 2 graphs, G and G prime, is able to model both the structure shift and attribute shift, thus addressing the challenge of complex distribution shift. And based on these Gaussian processes, eventually we would make predictions based on the GP posterior, which is shown on the bottom of this page. So skipping the theoretical analysis, and next are some experimental results. First, in a simpler case where we are transferring from homophilic to homophilic graphs or from heterophilic to heterophilic graphs. The last row is associated with GraphGP, our proposed algorithm based on the structure-aware Gaussian process, and its performance is the best in most of the cases on the target graph. We've also performed the comparison in a more challenging case where we're transferring from heterophilic to homophilic or the other way around. The results are shown in the top two figures where the red bar is corresponding to the GraphGP algorithm. And as we can see, its performance is better than the others in terms of the R-squared measure. Finally, I'd like to conclude and very briefly talk about some other directions. In this talk, I have introduced our recent works on addressing the multifaceted robustness in transfer learning. This is in response to the two types of vulnerabilities of current transfer learning techniques. One is the vulnerability to adversarial attacks, and the other is the vulnerability to complex distribution shift of rich data, such as graphs. Extending from all these works introduced in this talk, there were two major directions. One is to design a unified mechanism to handle both IID data and non-IID data. The other one is to go beyond robustness and further consider privacy, fairness, and transparency, basically the trustworthy transfer learning. And all of these belong to the bigger umbrella of trustworthy AI, essentially in enabling the wider application and adoption of state-of-the-art AI techniques in the presence of, say, dynamic environments, open world AI, or for physics-informed AI, and so on and so forth. The work presented in this talk is largely driven by my former PhD student, Jun Wu, who is currently an assistant professor at Michigan State University, and my current PhD student, Mr. Wenxuan Bao. With that, I would like to stop and take any other questions you might have.
Thank you so much, Dr. He. And it's a fascinating research what you and your team has done. I think we'll open up Q&A question right now, and let's see if we can able to take some questions. Let's see. I see a question here. Could you please explain more on adaptive parameter propagation for Fedora? Specifically, there is a min number of clients that are required for client K to optimize the transfer knowledge. Also, are there any specific measures used to measure distribution similarities for clients K and K prime?
I don't think I talked about Fedora in this presentation.
Is it? I'm not sure how this question came, but
it is one of the papers that we have published at, I believe it was TKDD of last year, but in this talk, I didn't sort of introduce that. Is for the federated learning setting. Yeah, so basically we approach federated learning from the perspective of transfer learning. And so I don't know if we could leave the questions offline.
That's okay. We can do that offline. But let me ask another question. I think I'm happy to see that you are looking at both the shift in the structural as well as the attribute shift. And I do work on a lot of energy-related time series data. And when you talk about these shift, what have you looked into in your research in terms of temporal? Like how often do you look at these windows for transfer learning? How do you see the shift is varying? What kind of it looks like you have elements of complex distribution shift could be captured using what you have, but you're also making two assumptions in your distribution informed neural network. One of them is this infinite layer for the width of neural network, and I'm just curious to see how should in a future when we look at especially this energy time series data, when we look at networks of all these distributed energy resources, and the temporal scale of these adversarial attacks is humongous, and it's complex, and it has heterogeneous, and there are multiple attributes, and we're looking at and did you look at multidimensional attributes for each of these? I know I'm loading up all these questions in one, but I think the simplest question would be how often do you see this shift in your two data sets? Yeah.
How often do I see these two distribution shifts in my data sets? So in our experimental evaluations, we have used a lot of the benchmark data sets where we do have those kinds of distribution shifts, meaning that between the source and target, and the work is focused on the graphs for the structure-informed Gaussian process. And there is topology shift in terms of the change of the structure And the underlying node attributes also has changed from the source to the target. In terms of the temporal data, that's a very good question. That's the aspect that I didn't mention during my talk. So the complex distribution shift not only appear on graph data, it also appears on the temporal or spatial temporal data. And we have done some work addressing different aspects for temporal data or spatial temporal data. I'm going to provide a few examples here. So in the past, we have been looking at the continuously evolving target domain. Right now, we have a typical sort of problem setting is where we have one source and one target, but in practice, it could be the case that a target is slowly evolving over time, and we might have just one single source domain. And in this case, we have converted this problem into multiple transfer learning problems, and we have leveraged the use of meta learning to help us adapt the model to a target domain in the current timestamp. So that is one aspect. Another aspect is we recently looked at time evolving graphs. And so we want to identify the out of distribution robustness of those temporal graphs. And the key idea is what kind of time invariant factors can we extract from those temporal graphs? So as I mentioned, one major group of the transfer learning algorithms is based on the invariant representation learning, where we want to identify a latent representation space to project all of our examples to, so that we can use a single predictor model to predict the labels for source and target examples with good performance. However, when the temporal aspect is at play, we want to extend this invariance to the temporal dimension, basically identifying what is not changing over time, what remains the same over time. And from there, try to come up with a slightly updated model from time to time to achieve the goal of continuous transfer. So
Great.
I also provided a lot of information, but I don't know if that answered your question.
I think it does. It does answer the question. I have another interesting question, but maybe I'm confused between these terms. Well, how do you see this concept drifts versus the distribution shift? When we talk about adversarial attack, I see a lot of online learning with this, variations of patterns of concept drift. And how do you read that in a concept drift versus the distribution shift? And in terms of, for labeled data, it makes sense. For unseen attack patterns, unseen adverse attack, or that is hidden somewhere, and how do we try to model them?
Oh, okay. That's a great question. I think at some place I talked about the covariance shift assumption. That's
yes, that's okay. Covariance. Yes. Okay.
Let me see.
We had a Google speaker who also talked about covariance shift using.
Yes, here is the mention of the covariance shift. Basically, we assume that the posterior distribution of the label Y given X remains the same between the source and target, but the marginal probabilities are different from the source to the target. And there are other finer scale definition of the distribution shift. And label shift is another one, which I introduced when talking about the BOBA algorithm. So in that case, we assume the class conditional distribution is being shared by the different clients, basically the Q functions, but the proportion label distributions are different as well. So researchers have also studied the concept of shift, which is along these directions in terms of studying what remains the same in terms of probability distributions from the source to the target and what's changing. And so basically, from the source to the target, everything could change, right? Especially in terms of the joint distribution of the features X and the labels Y. But a lot of the existing algorithms, transfer learning algorithms, they are not universally applicable to all kinds of shifting scenarios. They are best suited for a specific type, assuming the class conditional distribution is remaining the same across different domains, and the other algorithms could make a different assumption. So that's their that's the sort of the working conditions of the different algorithms.
Cool.
Yes.
Thank you for the elaborate answer. I have another question. Have you experienced a catastrophic forgetting problem? How does one deal with the issue when working with transfer learning?
That's a very good question. So, catastrophic forgetting is indeed very important um, challenge, especially when we're dealing with the time evolving domains. I think this is one of the major challenges in continual learning. And we sort of encountered a similar sort of challenge when we performed the research on continual transfer learning, where the source is remaining the same and the target is evolving over time. So we have this underlying mechanism of remembering the important information that has learned from the historical target domains to make sure that it's not being sort of forgotten when performing the learning of the predictive model for future timestamps. But I really didn't get into that in my talk today. It's more along the dimension of the continuous transfer learning.
Super. In closing thoughts, and you talked about future research and research in trustworthy transferable learning. Could you shed some light? One, how should students or future researchers should look into actually dealing with privacy, and choosing between or trade-off. How do you do this trustworthy transferable learning when you want to do some trade-off between this fairness and privacy factors that you mentioned? Very gentle question, but I think, yeah.
Yeah, so this talk, I've mainly focused on the robustness aspect of transfer learning, robust to adversarial attacks and to complex shifts. In terms of the privacy, I think federated learning provides a very good overall framework to protect the privacy of individual clients. Like I mentioned, they don't have to share their raw data, but rather they would share the knowledge with the central server and then eventually with the clients. And furthermore, there is the possibility of using differential privacy within federated learning to further protect the privacy of individual clients. And so that's one aspect of the privacy. I also mentioned the fairness, in particular in the context of transfer learning. If we have the fairness, demographic fairness, for example, satisfied in the source domain, okay? Can we ensure similar fairness in the target domain? And I think this also is applicable in the context of large language models, right? If you start with a small model, which behaves well and aligns with human preferences, after you use this small model to obtain a large model, can you ensure that these nice properties remain? And the last one is transparency. So at this point, we just sort of study whatever works in the context of transfer learning, and then study the connection of the generalization performance with certain sort of assumptions, say covariate shift assumption. But eventually, we need to know what is being transferred from the source to the target. Can we explain this in a way that can be understood by humans, especially those without intimate knowledge of AI or machine learning? For instance, these days we're collaborating with researchers in agriculture, and sometimes we want to use neural representations in our model. But then our collaborators would be asking the question of, what exactly are the neural representations? What are their intuitions? What do they mean? And if you include those neural representations in a, say, autoregressive model, and some of them have a very large coefficient, what does it mean? So is it tied to a specific factor that is consistent with their domain knowledge? And at this point, it's very much a challenge for us to understand how those neural representations factor into sort of the known knowledge. And that's why I mentioned the aspect of transparency in the future directions.
Thank you so much, Dr. Jingrui. I think we're going to conclude the webinar with this, and you will receive a nice plaque from our dean and from our UND, and thanking your time for this morning. I appreciate it. I think we should find ways to collaborate on proposals, I think after. So I think you have a great topic that you're working on and good. So I think we'll be in touch how we should
That
find.
sounds great. I very much look forward to that. And thank you again for inviting me.
Take care. Thank you.
All right, bye.
Bye.